Now, Kepler's third law is actually probably the most complicated one to look at, especially because of all like these math symbols appearing everywhere. But it's mostly just proportionality. So one special case is that um, the period of the period of a planet is equal to some constant times by its radius of orbit. So I'll just write that just to be sure because I didn't write it here. This is orbital time, and the r is orbital radius. So if we let k equal 1, t has to be in years and r has to be in astronomical units. It's a rough estimation if you remember, if you do inferential. I know this is quite random, but this is similar to normally you let the error approximation equal 1 over n, but then you learn the more accurate one, which is really depends 1.96 sigma over root n, or really whatever way you want to do it. But at that point, you start off with something simple and then it advances to something a bit crazier. Again, this is the same thing. Instead of going from t squared equals r cubed, we go to t squared equals 4 pi squared r cubed over gm, which in a simpler way can show that time is proportional to the 3/2 power of the radius. But it tends to be written as t squared is proportional to r cubed, as Kepler's third. Uh, this t equals 2 pi r to the 3/2 of gm is not really used that much. We tend to use the t squared form. The proof of this is actually it's a bit interesting, which is why I included the proof. Here's the proof. So when considering um, part of a planet's orbit, so as it's going around, this force is the gravitational force between these two. So this is the g m1 m2 over d squared bit. But this is also equal to the centripetal force, which we can write as m or omega squared, because we need the omega for 2 pi over t. Uh, this is also tangential. So I'm going to the proof. So we know that this is true. The centripetal force is the gravitational force, which we can write as m or omega squared. We know omega is 2 pi over t, so we can stop that in. I sort of skipped a bit here, but if you multiply by r squared, you get r cubed times 2 pi over t all squared, which then becomes 4 pi squared over t squared times r cubed, which is what we have over here. And then if we multiply by t squared divided by gm, we get t squared is 4 pi squared r cubed. We're going to look at an example of using actually the simpler form first. And I don't have one for the complicated version. Um, but it tends to be using the approximation anyway for most real world scenarios. Not real world, but like certain investigative scenarios, we tend to use it because we can use AU in years rather than meters or whatever. Uh, so that's really it. That's Kepler's third law.